Hello all, I am Saraswati, working as Associate Professor, Department of ECE, KS Rangaswamy College of Technology. Course name is Control Systems Engineering. Today we are going to discuss about mechanical rotational systems. What is mechanical rotational systems? The mechanical rotational systems means moving with respect to fixed axis. It consists of three basic elements. First one is moment of inertia, second torsional spring, third dashpot. The weight of the mechanical rotational system is represented by the moment of inertia of the mass. The moment of inertia of the system is considered as the center of gravity of the body. The torsional spring means the elastic deformation of the body. Dashpot means the friction existing in rotational mechanical system. The dashpot is a piston rotating inside a cylinder filled with viscous fluid. When a torque is applied to the mechanical rotation system, what happens? It is opposed by opposing torques due to the moment of inertia, elasticity and friction of the system. So by the Newton's law of motion, the applied torque and opposing torques are in opposite direction. Therefore, the algebraic sum of torques acting on the system is 0. The Newton's law states that the sum of applied torque is equal to the sum of opposing torque on a body. Let's see the torque opposed by three basic elements. So discuss one by one. The moment of inertia. So this is ideal mass element. In translational mechanical system, the mass stores kinetic energy. Similarly, in mechanical rotation system, moment of inertia stores kinetic energy. Now consider an ideal mass element which has negligible friction and elasticity. The opposing torque due to moment of inertia is proportional to angular acceleration, where T is the applied torque, Tj is the opposing torque due to moment of inertia of the body. So Tj is proportional to alpha and Tj is equal to J alpha is equal to J d square theta by dt square. By Newton's law, the sum of applied torque is equal to sum of opposing torque. Therefore, T is equal to Tj is equal to J d square theta by dt square, where J is the moment of inertia constant. So next, torsional spring. In translational mechanical system, the spring stores potential energy. Similarly, in mechanical rotational system, torsional spring stores potential energy. Now consider the ideal elastic element, torsional spring as shown in the figure, which has negligible moment of inertia and friction. So where T is the applied torque, Tk is the opposing torque due to elasticity of torsional spring, K is the torsional spring constant, theta is the angular displacement. So let the torque be applied on the torsional spring. The torsional spring will offer an opposing torque which is proportional to angular displacement of the body. So Tk is proportional to angular displacement theta. So theta is Tk is equal to k theta. By Newton's law, sum of applied torque is equal to sum of opposing torque. Therefore, T is equal to Tk is equal to k theta. When the torsional spring has angular displacement at both ends, theta 1 and theta 2, the opposing torque is proportional to differential angular displacement. Therefore, T is equal to Tk is equal to k into theta 1 minus theta 2. So next, the dashpot. So dashpot Consider the ideal frictional element dashpot, which has the negligible moment of inertia and elasticity. So therefore the opposing torque is proportional to angular velocity of the body, where Tk is the opposing torque due to the rotational friction of the dashpot, B is the rotational friction coefficient, omega is the angular velocity, theta is the angular displacement. So when the torque is applied on dashpot B, then it is opposed by an opposing torque due to the rotational friction of the dashpot. So this opposing torque is proportional to the angular velocity of the body. So Tk is proportional to omega, Tb is proportional to omega, dB is equal to B omega is equal to B d theta by dt. By Newton's law, sum of applied torque is equal to sum of opposing torque. So therefore T is equal to Tk is equal to K d theta by dt. So now when the dashpot has angular displacement at both ends, the opposing torque is proportional to the differential angular velocity. Therefore T is equal to Tb is equal to B d by dt into theta 1 minus theta 2. Now we solve the problem. Write the equation of the motion for the given mechanical rotation system. Obtain the transfer function of the system. So the given diagram is mechanical rotation system. So there are two moment of inertia J1 and J2. So the Laplace transform of torque is equal to T of S. Laplace transform of theta is equal to theta of S. Laplace transform of theta 1 is equal to theta 1 of S. So here in the system has two nodes, and they are the masses with moment of inertia J1 and J2. So the moment of inertia, the J1 be the angular displacement theta 1. This is the free body diagram of J1 as shown in the figure. Here the opposing torques acting on J1 are Tj1 and Tk. So Tj1 is equal to J1 theta square d square theta 1 by dt square. Tk is equal to K into theta 1 minus theta. By Newton's law, the sum of applied torque is equal to sum of opposing torque. Here the torque is applied to the moment of inertia of mass J1. So the J1 plus Tk is equal to T. So J1 T square theta 1 by dt square plus K into theta 1 minus theta is equal to T. Now taking the Laplace transform of equation 1 with a zero initial condition. So J1 S square theta 1 of S plus K theta 1 of S minus K theta of S is equal to T of S. So the common terms, theta 1 of S taking outside. So J1 S square plus K into theta 1 of S minus K into T of S minus K into theta of S equal to T of S. So next consider the moment of inertia of mass J2. So this is a free body diagram of mass with moment of inertia J2 has the angular displacement theta. The opposing torques acting on J2 are J2, Tk and Tb. So Tj2 is equal to J2 d square theta by dt square, dB is equal to B d theta by dt, Tk is equal to K into theta minus theta 1. So by Newton's law, sum of applied torque is equal to sum of opposing torque. So here Tj2 plus Tb plus Tk is equal to 0. Now this J2 d square theta by dt square plus B d theta by dt plus K theta minus K theta 1 equal to 0. Now taking Laplace transform with a zero initial condition, J2 S square theta of S plus Bs theta of S plus K theta of S minus K T1 of S equal to 0. taking common terms, theta of s. So j2 s square plus bs plus k into theta of s minus k theta 1 of s equal to 0. So from this equation, we find out t1 of s. So t1 of s equal to j2 s square plus bs plus k divided by k into theta of s. Substituting for t1 of s from the equation 3 in equation 2, we get j1 s square plus k into j2 s square plus bs plus k minus k square whole divided by k into theta of s equal to t of s. From this expression, we find out transfer function theta of s by t of s. The transfer function is nothing but Laplace transform of angular displacement divided by Laplace transform of torque, applied torque, equal to k divided by j1 s square plus k, j2 s square plus bs plus k minus k square. So this is a final answer. So next topic, electrical analogous of mechanical rotational systems. The two systems are said to be analogous to each other if the following two conditions are satisfied. The two systems are physically different. The differential equation modeling of these two systems are same. So then the system is called as analogous system. The electrical systems and mechanical systems are two physically different systems. There are two types of electrical analogous of mechanical rotation systems. One is torque voltage analogy, second torque current analogy. Analogous elements in torque voltage analogy. The torque in rotational mechanical system analogous to voltage in electrical system. Moment of inertia is analogous to inductance in electrical system. Rotational friction coefficient in mechanical rotation system is analogous to resistance in electrical system. Torsional spring constant in rotational mechanical system is analogous to reciprocal of capacitance in electrical system. Angular displacement is analogous to charge in electrical system. Angular velocity in mechanical rotational system is analogous to current in electrical system. Next, analogous elements in torque current analogy. The torque in mechanical rotational system is analogous to current in electrical system. Moment of inertia is analogous to capacitance in electrical system. Friction coefficient is analogous to reciprocal of resistance in electrical system. Torsional spring constant in rotational mechanical system is analogous to reciprocal of inductance in electrical system. Angular displacement is analogous to magnetic flux in electrical system. Angular velocity is analogous to voltage in electrical system. Thank you.